Okay, so in this last part, I will discuss a case where we applied random matrix theory to a spatial network. And in particular, we were interested in a problem of metapopulations. So metapopulations are population of a species that live on patches in space that are spatially separated. And the important point is that in a metapopulation, there is a separation of time scale. There is a fast time scale that is the local dynamic, so what happens on an island, and there is a a long time scale that is dispersion. So since you have this separation of time scale, the only thing that matters on the local scale is whether the species is present or absent. So you can imagine that there is some carrying capacity, the species goes there, but there are fluctuations, and the species can go locally extinct. So there are two behavior. There are two regimes in this model. In these models, typically one regime where the species goes globally extinct if dispersion is small enough, because like everything goes locally extinct with a given rate, and then there is no time for dispersion to repopulate empty islands. And then there is another regime, which is an active regime, where dispersion is large enough so that you can repopulate the islands and the system is active. You have a non-zero probability to find species on the system, in each island, sorry. And the important point is that in these kind of models, what is really important is the eigenvalues of the dispersion matrix. So the dispersion matrix define what is the probability of going from an island to another island. And if this eigenvalue of this dispersion matrix is larger than the death rate, than the local extinction, you persist. So we translated this problem in a random matrix theory problem. We have a set of islands at a random points in space, and the probability of disperse to migrate from one island to another island is the product of their size times a function that decays with the distance. And so in principle, if you look at this larger eigenvalue that determines the capacity or the persistence of the populations, you find a dependence on everything. So here I'm plotting versus the dispersal length, so how far you go, and then there are like different number of patches on this space, different dimension. We have 1, 2, and 3. You have different kernels. You can have like decays exponentially as a Gaussian or other things, and different variants of the size of the island. You can imagine that you can have islands all of the same size or of different sizes, and this matters in these terms. So they all depend on each other, but using random matrix theory, actually what you can find is that all these curves collapse to a single curve, and the only thing that matters is actually what is the sort of effective number of neighbors, which is the sort of effective rate at which things migrate to you, times the an effect that depends on the variance of interaction strength. And so you have actually one effective parameters that make all these things collapse. And here there are deviations and can also be described using these effective parameters actually. So this concludes this lecture on applications of random matrix to ecology. I hope that I gave you a sort of overview of the tools that are used in random matrix theory and the kind of problem you can attack with random matrix theory. Of course, I only discussed applications to ecology, but you can imagine to apply to almost any field of biology where you have a large number of agents interacting, or beyond biology, or sociology, economics, and so on. And I want to thank you for your attention. Thanks all the collaborators that helped me and collaborated with me on these applications of random matrix theory to ecology. And I hope you enjoy these lectures.